Hey programmers, Alvin here. Right now I want to go over a code solution in Python for this how high problem. And so we'll jump right in over here. Hopefully you already watched the approach video. If you didn't, I recommend you go back and watch that before you look at the code solution. Because we're just going to implement that pretty straightforward. So we're going to start with our base case, and in the approach video we mentioned that, hey, the key insight is whenever we have like a null or none, a pointer, or an empty tree rather, then we can say that the logical height of that tree is -1, right? Because that's a really, really important aspect. And I think also in the prompt, one of the test cases actually has that explicitly, right? When they pass along none, represents the empty tree, should return -1. So that's kind of a dead giveaway. So that'll be our base case for this recursive solution. It's going to operate very similar to a depth first traversal, right? So I'll say if my node is none, then what I'll go ahead and do is just return -1. Nice. And now I'll lay down my foundational depth first code. So I know that any flavor of like depth first has to make recursive call on node left, likewise for node right. And now I'll stay focused on, this specific function now. I know that this function is recursive. It's going to return a number. So the number I get back from these recursive calls, this must represent the height of that subtree. So I'll maybe save this to a variable, and I'll call this my, left tree height. So that's the height of my left subtree. Likewise, my right tree height. You can skip these variables if you're not a fan of them. But now that I have these two numbers, we mentioned in the approach video that we need to determine which of those subtrees is larger, right? As the parent, I'm going to choose or determine my height based on the height of the taller child I have. So the taller between my left and right. So if you wanted to, you could write maybe just an if statement checking like if left tree height is bigger than right tree height. But my favorite way to implement this pattern to pick the larger is to just use max in Python. So maybe a quick aside we'll do is I can use the built-in max function in Python. And I think you can pass along some comma separated things. So I'll give it some numbers, maybe like 5, 2, 12, and 11. And I'll print out what this gives back. And I'll just run this as a script. See what we get here. And we should just get the answer 12, right? Nice, and there we see we chose a 12 correctly there. So I'll just use the max function to choose the correct height. So I'll take max of my left tree height as well as my right tree height. And whichever number I choose, my return value as the parent needs to be 1 plus that larger value, right? And the reason I do an additional 1 and I add that to my child's height is if I'm the parent of a subtree, then there is one edge that separates me from my child, right? And I count that edge with a 1 plus, right? So this is a really important thing to do. And so with that, this should be a fine solution. Not too much code at all. Let's run the tests for this. Nice, and it looks like we pass all of the test cases, right? Like we said, the runtime of this is pretty good. In terms of the time complexity, we're just making a recursive call for every node of the tree exactly once. So if we say n is a number of nodes, and this is an O of n runtime solution, just doing the max operation, that's going to run in technically constant time as well, because I'm only checking for the max between two things, right? It's always 2. 2 is a constant number, so it doesn't attribute to my runtime. So there we have the solution. What I recommend you do is if you had any issues with this how high problem, definitely, linger on it a little bit more, maybe take a break or redo the problem, because this kind of depth first variation is super common for our binary tree problems, and you want to master this one before moving on any further. So give it a go on your own.